Again, there are many characteristics, about a dozen of them, that you need to go through to prove that you have a vector space. Okay? And we talked about the idea that the polynomials can form a vector space. Okay? They have many of the same, well, they have all the same characteristics under addition and multiplication by constant numbers that column vectors do. Okay? So anyhow, if you add two vectors, you get a vector. Okay? So, and then we talked about it last time. If your vectors are polynomials, if you add two polynomials, you get a polynomial. We'll write that out and we'll establish it. An additive identity exists. That means a vector that you can add to any given vector, that you get the same vector back. Okay? And inverses. Exist. What do I mean by additive inverses? I mean two vectors that you add up to get 0. Okay? The additive identity is your 0 vector. And additive inverses add up to the 0 vector, okay? Now let's just consider the integers. 1, 2, 3, 4, 5, and so on. 0, -1, -2, yeah, okay. All the whole numbers and their negatives. Okay? Do they satisfy these? If those are your vectors, I mean, you don't really want to think of them there, but you could, just on the number line, let a vector be the arrow from 0 to that, whatever that number is, right? Okay? And hopefully you did that in elementary school at some point. Okay? Like you add 5 and -2 by going a vector 5 and a vector -2, giving you vector 3, right? So those are one-dimensional vectors. So integers can be treated as one-dimensional vectors. Okay? At least as far as these conditions go, because if you add two integers, do you get an integer? Well, so far integers are vectors. Is there an additive identity? Like, what would I add to 15 to get 15? Let me think. 0, right? So your 0 vector is just the number 0, the integer 0. Additive inverses, what's the additive inverse of 15? -15, right? Okay, so far our integers form a vector space. And it turns out that they fail one of the conditions later, okay? Real numbers do form a vector space. Now you got to be able to multiply them by any real number. And any number in a given field, but that field's always going to be real or complex numbers. And get 1. So if I multiply an integer by 1/2, well, if the integer isn't even, I don't get an integer, do I? So you got a problem there, okay? So multiply if you multiply by a real number, you get a vector, okay? Again, it's not always real numbers, okay? Could be members of any field, but you don't know what a field is and you're not going in this course, okay? Except complex numbers. They form a field too. So you can say the same thing, but this is where the real numbers fail. So these are satisfied. I'm not the real numbers, the integers. These three are all satisfied by a set of integers, right? So there's one example of something that looks pretty good with these characteristics, but fails in this one, okay? Now, you also have an associative law, and there are actually a couple of associative laws, and we're not going to worry about those right now. Because for one thing, they're kind of tedious to prove, but they're not that hard to understand, okay? And more, okay? So let's just look at these four characteristics right here. Okay. And let's consider a set of ordered pairs. It's a set of X five X, where X is a real number. Now, if I give me an example of an ordered pair that satisfies this.
315.
Can you?
315.
315. And Cole, give me an ordered pair.
420.
420. 420. I mean, I know what it is, but just make sure you're saying it right. Okay, 420, right?
Yes.
Okay. Now, just taking these two as an example, and examples don't prove anything, but just seeing why we expect that these characteristics will all behave, or will all work, okay? And it's a good way to start. If you're asked to show that something is a vector space and it's unfamiliar, pick a couple of typical members, nothing unique about them. You know, if you can do that. Sometimes it's hard to figure out just what would be unique and what wouldn't. But you just pick two representative numbers that aren't related in any special way, or representative elements of your set, and see if these things work. So if I add these, what do I get?
730.
Okay, well, this plus this, okay? And we're using, you know, I haven't written out rigorous definitions, okay? 315 plus 420 is 735. Well, is that in this set?
Yeah.
Yeah, if X is 7, 5X is 35, and that's it, right? Okay, now that doesn't prove it's always true for all integers, but it's easy to do that. You just write some symbols, okay?
Yeah.
I mean, for all ordered pairs of real numbers, okay? additive identity. What's the additive identity?
0.
Sorry?
0.
Oh, you can't add an ordered pair to 0. You can only add ordered pairs to ordered pairs.
0, 0.
Yeah, that's what you meant. Okay. Okay, so adding 0, 0 is clearly not going to change anything. Now to write out a proof, we got to write it out so that we're sure it's true. Even if this is the square root of 487 and 5 times the square root of 487, right? It's still going to work. And it's obvious that it will, but you know, we can't just say it's obvious because of the example. But the example helps us understand why it's true. Okay, what about additive inverse? What would an additive inverse of 420 be?
-4.
Yeah. And that is your additive identity, so these are inverses, right? And if you multiply by a real number, so what would you want to multiply one of these by?
2.
Huh?
2.
I don't want to use 2. It's an integer, it's kind of unique.
4.5.
4.5?
Yeah.
I can't multiply by anything that big. How about pi?
Okay.
Okay? Because then I don't have to do any arithmetic, I just write down,
Yeah.
you know, you can't write down pi exactly as a decimal, so you're just stuck writing pi. I'm going to go to something that actually is a little closer to proof. I'm going to say pi times x 5x equals what?
X5, 5x5.
That equals pi x 5 pi x, right?
Right.
So and 5 pi x is 5 times pi x, so this is 5 times this, right?
Mm-hmm.
Okay. That doesn't prove it either. But if I wrote instead of pi, I wrote c, where c could be any real number, what would I get? I'd get cx, 5cx, right?
Right.
And this is still 5 times this, and that would prove this property, right?
Right.
Okay? So it works out. Okay? Now, you would want to write it out in symbols, and we'll, you know, deal with that probably next time. But this helps us understand how these properties are used to test for a vector space. Okay.